proceed. Okay, so here we now have also the term which we call relative density. Okay, so the relative density is commonly used to indicate the in situ, the on-site, no? In situ, that means the condition on site, in situ. So that indicates the in situ denseness or looseness of the granular soil material. Okay. Um, as when we say granular soil material, that's basically this sands, no, and yeah, sands and gravels, for example, no, materials in some silts. Okay, we try to divide between granular soils and cohesive soils. Okay, yeah. As of the moment, let's uh, just consider the term relative density with respect to granular soils, no? Sands, gravels, and some silts, okay, for example. Okay. Now, so the relative density is defined, okay, so that's D sub R in percentage, okay, that's defined as the maximum, the ratio of the difference between the maximum void minus the C to void ratio over the maximum void ratio minus the minimum void ratio, where the void ratio is the in situ condition, okay, on site, and then the maximum void ratio of the soil in the loosest state, okay. Okay, so that means there are a lot of voids, no? Loosest state, lot of voids, so that's the maximum void ratio. And then the minimum void ratio is the void ratio of the soil in the densest state. No? So there's a very small voids. No? Okay, very small because it's very dense, no? Very compacted. Okay. So later on in the lab, you will also be doing compaction test. No? Okay. In the laboratory. Okay. So the values of the relative density may vary from a minimum of 0% for very loose soil, a maximum of 100% for a very dense soil. Okay, because when you talk of a relative density, we basically have the terms very loose, loose, medium dense, dense, and very dense conditions. Okay, and they have their corresponding relative density values. Okay. Um, okay. So, for example, this one here, we have now the different relative density descriptions. Okay, for a granular soil deposit. Okay, for say sands and gravels, for example. Okay, so for very loose, that's from 0 to 15% of relative density. Then from 15 to 50 is loose condition. 50 to 70% of relative density is a medium dense condition. And then 70 to 85 is a dense condition. And then 85 to 100% is a very dense condition. Okay. So, so in place, no? So in place soils, okay, or in situ soils seldom have relative densities less than 20 to 30%, okay, while compacting a granular soil to a relative density greater than about 85%, for example, is already quite difficult to achieve, no? In the field, okay, depending on the compaction equipment, okay. Um, because when you have 85%, that's already a very dense condition. Okay? In the field, when you do compaction, if you can already have a dense condition, then that's already at least good enough, no, as far as construction is concerned. For example, no? When you do earthworks, no? Especially with earthworks in roads, for example. Okay. Yeah. So, okay, so I guess we now have some examples here. Okay. So let's just try to apply the formulas that we have learned so far. Okay. Although my colleagues will give you probably more examples this Thursday. Okay. They can probably expound on this more with the examples that they can provide to you. Okay. Okay, so here we have an example problem. Okay, the saturated unit weight and the water content in the field are found to be 18.55 kilonewtons per cubic meter. The unit weight and the water content is also 33%. Okay, so here we can also consider it to be a saturated water content. Okay, so we in this problem we are asked to determine the specific gravity of the soil solids and the field void ratio. Okay, although in practice we normally have the specific gravity, no? In practice. Okay, okay. But just for the sake of discussion. Okay. So since the saturated unit weight and the water content are both ratios, okay. So since we don't know the total volume as well, in the next problem we'll be given some dimensions where we can compute the volume of the soil sample. But in this case, in this problem, since we don't have the total volume of the sample, then we can probably assume. We can probably assume a unit total volume equal to 1 cubic meter. So which means that this problem can be, if we just go back, it can be treated like this. This phase diagram. So you have a saturated soil sample, and then we consider the total volume to be 1. Okay, so you can expect that we will be using some of these formulas, for example. Okay. Okay, so the given is the saturated unit weight is 18.55 kilonewtons per cubic meter. Okay, and then the saturated unit weight is equal to 33%. Okay. Okay. So again, to recall from equation 3.9 from the previous slides. Okay. Again, don't worry, all of these are just taken from the book. Okay. So the unit weight is equal to the total weight over the total volume. Okay. Um, but in this case, since the volume is equal to 1, okay, is equal to 1, so the saturated unit weight is just equal to the total weight, which is equal to the given, which is 18.55 kilonewtons. Okay. So the total weight is again equal to the weight, sorry, if you can see my cursor, is equal to the weight of the soil solids plus the weight of the water. Okay. So, but the weight of water is equal to this. We know that the saturated unit weight can be is equal to the weight of water over the weight of soil in a saturated condition. Okay, uh, we are presuming that we have a saturated because we are given a saturated unit weight. Okay, so that's a saturated condition. Okay, so that means that the weight of water is equal to the saturated unit weight multiplied by the weight of soil. Okay, so if I just factor out the weight of the soil solids, that's equal to 1 plus the saturated water content. Okay, so Okay, so from this equation, we can have now the weight of the soil solids is now equal to the total weight, okay, total weight divided by 1 plus the saturated water content. Okay, so we have the given the total weight is 18.55 kilonewtons per cubic meter. And then the saturated water content is 33%. Okay, so but in the formula we use the decimal form. That's 0.33. Okay, so that means the weight of the solids is equal to 13.95 kilonewtons. Okay, so that means the total weight, if the total weight is 18.55, the weight of the soil solid should be smaller, no, than the total weight. Okay, so that's 13.95. Okay, so that means that if this is now the total weight, and this is now the weight of the soil solids, so by definition, the total weight is equal to the weight of the soil solids plus the weight of water. So then we can also derive the weight of water, which is equal to the total weight minus the weight of the soil solids. So if we just substitute the values, then we can get the weight of the water, which is equal to 4.6 kilonewtons. Okay. Okay. Now, considering that the unit weight of water is 9.81 kilonewtons per cubic meter, so by definition of unit weight, so we know that the unit is defined as, or sorry, the unit weight of water is defined as the weight of water over the volume of water. But we know that the weight of water is 4.6 divided by 9.81, which is a given. We know that. Even in fluid mechanics, it's the same. So the volume of water is now equal to 0.469 cubic meters. Okay. Okay. Now, since the soil is fully saturated, okay, fully saturated. So if you go back again from the diagram, if the soil is fully saturated, we know that the volume of voids is equal to the volume of water. Okay. So if you go back, so we know that for a fully saturated condition, we know that the volume of water is equal to the volume of voids. Okay. So that means the volume of solids, okay, is now equal to the total volume. Okay, sorry, here's my cursor. The volume of solids is now, I hope everybody can see my cursor. The volume of solids is now equal to the volume of voids minus the volume, sorry, the total volume minus the volume of voids, because we know that the total volume is equal to the volume of solids plus the volume of voids. Okay. But we have presumed earlier that the total volume is equal to 1 cubic meter. Okay. Since we don't know the total volume, so that is 1 minus the volume of voids, which is just equal to the volume of water, which is 0.469. So that means the volume of the soil solids is equal to 0.531 cubic meters. Okay. So going back to the definition of void ratio, we know that the void ratio is defined as the volume of voids over the volume of solids, okay, wherein the volume of voids is 0.469 divided by the volume of solids, which is 0.531. That gives you a void ratio of 0.883. Okay, that's dimensionless. Okay, okay, void ratio. Um, so also for the specific gravity of the soil solids, we know earlier that it is equal to the weight of the soil solids divided by the volume of the solids multiplied by the unit weight of water. Okay, or that's basically the specific gravity is defined as the unit weight, or the specific gravity of a material is equal to the unit weight of a material divided by the unit weight of water. So in this case, our specific gravity is with respect to soil. So that's the unit weight of the soil, or that's the, by definition of unit weight, that's the total weight over the total volume. Okay. But we know that the weight, in this case, for the soil solids, we know that the weight of the soil solids is, yeah, this one, 13.95 divided by the volume of solids, which is 0.531 here, multiplied by the unit weight of water, will give us a specific gravity of about 2.67. And again, in practice, normally we get about 2.65 to 2.7 something, depending on the soil material. Okay? Um, we also provide that in the geotechnical report. Okay? So that means this value here is reasonable. Okay. Yeah. Um, okay. I think we have now solved the problem. Okay. So that's the specific gravity and the field void ratio. Okay. Do you have any questions or clarifications so far before I proceed to another example? There's something in the chat. Okay, so no questions so far. So I hope I am clear enough. Okay. If you have some questions or clarifications, please don't be shy. No, please try to ask. Okay. Again, take note. You are paying me to learn. Okay, for you to learn. Okay. Okay, if there are no questions so far, let me proceed to one more example. Then we can probably already adjourn. Okay. Oh, there's a chat here. Yes. Where did the WS formula come from again? Where's that? Where's WS? Okay. Okay. So okay. So this formula, I think you're referring to this formula here. If you're seeing my cursor. Okay. So it just came from here. Okay. So again, the total weight, okay, is equal to the weight of solids plus the weight of water. No? So if we go back to the diagram, um, okay, so this one, if we go back to this diagram, since the material is fully saturated, okay, so the total weight, apologies, no? There's supposed to be here a line, no, wherein there's a total weight, no? Just like this one, no? Volume. So here, there's supposed to be a total line for the total weight, wherein the total weight is equal to the weight of the soil solids plus the weight of water. Okay, I think for the other diagrams we have that. Let me see. Okay, here. Okay, here, for example. No? So the total weight is equal to the weight of water plus the weight of solids. Okay, so if we go back, so the weight of solids plus the weight of water, but we know by definition that the water content, okay, but the water content is defined as the weight of water over the weight of the solids. Okay, let me go back to that definition again. Where is that water content? Where did we have that water content? Here. So the water content is defined as the weight of water over the weight of solids. Okay. In this case, this is for a moist water. But the formula is the same if you have a so this is the moist water content in the case of a moist condition. Okay. A condition where you have water and air in the voids. Okay. But if the voids is fully filled with water, that means it is fully saturated. Okay. Uh, then the water content can be treated. No? In this case, it is called the moist water content, but in the case of a saturated water content, uh, the formula is still the same. No, it is the weight of water over the weight of the soil. Okay, so it's saturated water content. Okay, so depending. No, okay, so it can either be a moist water content or a saturated water content. Okay, so going back to the problem. Okay, so going back to the problem, then the saturated water content is equal to the water content over, sorry, the weight of the water over the weight of the solids. Okay. Yeah. So then the weight of the water is equal to the saturated water content, considering that we have saturated conditions. Okay. So then we just replace the weight of water by this one. Okay. So I hope that's clear enough. Okay. So from here, we just factor out the weight of the soil solids. Okay, that is 1 plus the saturated water content. Okay. So then we have an equation now wherein the total weight, okay, the total weight is now equal to the weight of the soil solids multiplied by 1 plus the saturated water content. Okay, so the total weight equal to this one. So then, if you want to get the weight of the solids, so we just divide the total weight by 1 plus the saturated water content. Okay, so that gives you these values here, wherein the total weight is just basically equal to the saturated unit weight, which is equal to 18.55, because by definition, the saturated unit weight is equal to the weight over volume, the total weight over the total volume in the saturated case. Okay, because it's a saturated condition. That means there's no air. Okay, but in this problem, since we don't know the total volume, we can assume that we can a unit total volume at unity. Okay, so the volume is equal to 1. So that's why um, that's weight over volume, but volume is 1. So that becomes the weight. The total weight is equal to the saturated unit weight. So that's why we have the same value, okay, for the saturated unit weight and the total weight. Okay, okay, so there's a chat here. Okay, so Kia. Okay, so I guess that's clear. When do we know to use the porosity void ratio formulas, or will it depend on the given? Okay, so basically, it depends on what is given. No, it depends on what is given. Okay, so that's why in this here, no? Depending on what is given, so in this case, now we were dealing with saturated unit weights, no, basically. No? Okay, in that case, what was given? Let's see, it was given again. What was given is the saturated unit weight and the water content. Then what is asked is the specific gravity and the void ratio. Okay, so okay, 4 terms. So that means you have the water content, specific gravity, and the void ratio. Let's see. Um, yeah, yeah. Okay. So in this case, it's yeah. There's no given here with the 3 terms combined. No? It's either what you have is the specific gravity and the void ratio, or the specific gravity and saturated water content, or you have the void ratio and the saturated water. 10. Okay. Yeah. So, mm, and then we are dealing with the saturated unit weight, right? Yeah, saturated unit weight. Okay. So, yeah. So again, it depends on really what is given, no? And that makes it quite a bit difficult, no? In problems, because you need to try to relate, no? Each of these parameters to one another. Okay. So you must try to understand the phase diagram. Okay. Yeah. Try to understand the phase diagram and their relationships. Okay. The figures that I have shown earlier. Okay. Yeah. So that's actually a very good question, but it's also a difficult question, no? Because that's usually the problem in the board exam. Okay. It's always a question of what formulas you can use depending on what is given and what is asked. Okay. But I guess over time, when you start solving problems and then you repeatedly solve problems over time, no, you can develop some patterns. No, now if this is the problem, this is how I approach it. If this is the problem, this is how it's being approached. Okay, so it's a question of practice. No? Problem practice of solving problems. Yeah, of course, at first it's always difficult. It's always difficult, but over time you will develop the habit of solving problems. Then you will be familiarized. For example, in the board exam, I think my colleagues here can also attest to that. Basically, the board exam is usahay swerte-swerte ra na siya, no? Usahay na yung mga problems nga pare-pareha sa imong gisolve. Okay? Pare-pareha sa imong gisolve. So, maswertehan ka lang na ang kato imong i-solve during the review, for example, pare-pareha sa imong nakita sa board exam. Okay? So then you get familiarized how to approach it. Okay? So the same here also. So if you practice many problems, then for example during the exams you can see a similar problem. Then okay, this is how I approach it. Okay? But if you don't practice solving problems, then it might become difficult. Okay, because it will become everything will become first time for you. Okay, okay? I hope I have answered that question. Okay, any more questions or clarifications before I proceed to another problem? Okay, you're welcome. Any more questions or clarifications? Okay, there's another one here. I hope everyone can see the chat. Okay, because I'm just sharing my screen. Sir, are extensive soil tests necessary for every site before building design and calculations are done? Or can it be simplified, especially if the site are small or if buildings are not very tall? Okay. Yeah, I think this is a very practical question. Okay. In practice, normally, um, we just normally do, no, we just normally do, we call them the routine test. Okay. The routine test, I think, I think in our next lecture, I think when we go to the, yeah, in the next lectures we'll be discussing some topics wherein in some of our lectures that I'll be discussing to you, these parameters are normally uh, the the geotechnical parameters, which we call them as the routine test, the basic test that we specify. I normally specify, no, when we do geotechnical investigations, depending on the structure. Okay. Um, in my experience, I've been dealing with critical structures. I'm not normally involved in buildings. I'm more involved in non-building structures, such as power plants, industrial plants, critical infrastructure, such as the Cebu Cordova Bridge project, In these projects, where we deem them to be critical projects, we have been dealing with renewable energy projects such as wind turbines. For example, here in in Luzon, for example, if you have seen in Facebook, where many people from Manila, they go there in Burgos, um, uh, where's this? In Ilocos Norte. Okay, if you have seen there the Burgos wind farm, we are the ones who designed and built that one. Okay, about 30 wind turbines. It now has become a tourist spot. Many Filipinos go there, take a picture of these windmills. Okay, so in that case, sometimes the tests are a bit extensive. Okay, also when we um, design and build solar power plants. Okay, with the solar farms. Okay, also with geothermal power plants. We also design and build them. In this case, we give extensive tests. Okay, but in some of our projects, such as manufacturing plants, okay, these are buildings, but these are more of manufacturing plants in Batangas. Okay, there's a site there where just about last 2 months ago, we were building a structure for Canon. Canon is the makers of Canon camera. We are building one of their manufacturing plants in Batangas. Okay, where manufacture these cameras. Okay, so in that case, for manufacturing plants, sometimes we just provide the routine test. Okay, the routine test I will explain later now as we go on with our discussion. I will go back to that. Okay, so it depends. It depends on the structure. Okay, um, sometimes we just specify routine test. Sometimes we add the what we call as the engineering performance test, no? Such as the shear strength test and the compression test, no? Depending on how critical the structure is. Okay, and then we put everything there in the geotechnical report, which I normally sign, and these geotechnical reports are the basis will become the basis of the designers, the structural designers. I think Engineer Sena here is into structural design. Okay, so in structural design, normally we structural designers they refer to the geotechnical report, no, which we provide as geotechnical engineers. Okay. Okay. I hope I have answered that question. Okay. 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 Before I entertain any more questions, let me just discuss one more problem. Okay. Because we might not have time. Okay, let me just discuss here quickly. Okay. Okay. Let's now A10. Okay. Okay. Let's just discuss this one more problem. Okay. So here we have a cylindrical soil sample prepared laboratory testing, which has a diameter of about 71 millimeters and a height of 142 millimeters. Okay, and weighs this amount here, 10.675 times 10 to the power negative 3 kilonewtons. It's a unit of force. I think this is a typical soil sample, no? Where when you do engineering performance tests, no? Such as um, consolidation, sorry, a triaxial test, for example, engineering performance test, which I just mentioned earlier. Normally, the sample that you bring to the lab is normally the height is about twice the width, no? Or the diameter rather. The diameter of the sample is usually a circular cylindrical sample. No? Okay, so it's usually these dimensions. Okay, so um, so here, if the degree of saturation is 93%, and the specific gravity of soil solids is 2.71. Okay, this is also realistic. Normally we get about 2.65 to 2.71 for specific gravity of the solids, soil solids, depending on the type of soil. Okay. And then here he mentioned that the degree of saturation is 93%. Okay. So again, if you recall, the degree of saturation is 100%, then that means you have a fully saturated water. Okay. So in this case, it is 93%. So it's not, that means it is not saturated. No? It is not also dry, so because it's not zero. Okay? But it's 93%. It's almost saturated. Okay. Or sometimes we call it quasi-saturated soil sample. Okay. So with this given, you are asked to determine the void ratio, the water content. In this case, the water content is the moist water content. Okay, considering 93% degree of saturation. And there, but for letter C, you're asked to determine the water content under fully saturated conditions. That means here you have desaturated water content, whereas in B you have the moist water content. And that means there's still air, okay, in that condition. So okay. So to solve for the void ratio, okay, so we are given the weight of the sample is 10.65, then 10 times 10 to the power minus 3 kilonewtons. And then you have the degree of saturation is 93%, and then the specific gravity of the soil solids is 2.71. Okay. Now, since you're given the dimensions of the soil sample, then you can compute for the volume, the specimen volume. We don't need to assume one. Okay, you can compute for the volume. That gives you this one here. Then again, we know that the total weight is always the weight of the water plus the weight of the soil solids. Okay. And then we also know these formulas here. Okay, so if you try to recall, the unit weight of water is the weight of water over the volume of water. The specific gravity is the weight. That's the unit weight of water. The degree of saturation is the volume of, finally, the void ratio is the volume of voids over the volume of solids. Okay. So we're just trying to recall these formulas, these basic formulas. Okay. So at least in the board exam, you must know them by heart, no? In the board exam. Because sometimes in the board exam, normally the examiners give very difficult problems. They will just give us until the basic formulas. Okay? For letter A, so okay, so we have here the total weight is now equal to the weight of water plus the weight of soil solids. Okay, but considering these formulas here, we can have the weight of water and the weight of the soil solids. So we try to substitute those formulas here. Okay, yeah. But considering now the volume of water, we also that the volume of water can be expressed using this formula here with respect to the degree of saturation. So I can replace the volume of water by the degree of saturation times the volume of voids. Okay? So I can replace the volume of water by this one here. Okay. And then this volume of voids, we know that the volume of voids can be expressed also by these terms here. So that means the volume of voids can be expressed by the void ratio times the volume of the solids. Okay. Yeah. So just factor out some terms. Then you can get this equation now for the total weight. Okay. And then here also, if we try to recall for um, the total volume, which is E plus 1, okay, if we recall now, if we go back to phase diagram, where was that? Yeah, this one here. So that's the total volume, which is 1 plus E. assuming that the volume of solids is equal to 1. Okay, so that's 1 plus E. So let's go back. Yeah. The total volume is equal to the volume of voids plus the volume of solids. No? In the case of a moist condition, okay, moist condition, okay. And then if we, so the void ratio is equal to the volume of voids over the volume of solids. Then one is just same as volume of solids over the volume of solids, no? Which is also equal to the total volume over the volume of solids. Okay. Before I continue, there's a chat here. Okay. Oh, I thought there's a question. Okay. Okay. Mm, so if we now try to substitute V sub S, okay, V sub S here in this formula, okay, then we can now get this formula here. Okay, so I will just leave that to you for the algebraic manipulation. Okay. So then from this formula, then we can just we can just substitute the given. So we know that the total weight is this amount here. Okay, this is the unit weight of water. This is the volume of the sample. Is that correct? Yeah. Point. Oh, sorry. Uh, 0.572. That's the volume. Sorry. So I think there's must be something wrong here. Anyway, so that's the volume of the soil. Okay, and then the degree of saturation that's given. That's a 93%. Okay, so but here in the formula we use the decimal form. Okay, we always use the decimal form. That's 0.93 E plus the specific gravity of the solid. Okay, um, over 1 plus E. Okay, so from here you uh, just do. You can use your calculator. Okay, you can do trial and error, or you can use quadratic formula if you like. Using algebra, then you can solve for the void ratio, which is 0.769. Okay. So we have solved problem A. Okay. So for problem B, okay. So for problem B, if for problem B, we can use this equation here. Okay, wherein we now know the void ratio. Okay, so we substitute here the void ratio plus 1 is equal to the total volume. So, okay, so this is indeed 0.562. No? So this must be 0.562. Okay, this is the total volume over the volume of the solids. Okay, so that's here. So from here, we can volume of the soil solids. Okay, from here. Okay, and then now that we have the volume of the solids, then we can now compute for the weight of the soil solids, which is given by this formula. Okay, by this formula, that's the specific gravity of the soil times the volume of the solids multiplied by the unit of water, which I think we have also derived this before. Okay, so then just substitute this is given, this is known, this is derived from here. Okay, so that gives you now the weight of the soil solids. So for the weight of water, we know that that's equal to the total weight minus the weight of solids, wherein the weight of solids is derived from here. We have calculated it. The total weight, where did we get the total weight? Okay, so the total weight is given. Okay, so that's this one here, that's given. So just subtract the two, will give you the weight of the water. Okay, so by definition of the water content, which is now the weight of water over the weight of the soil solids, so it's now this value divided by this value will give you 0.263, or that's a 26.3%, which is now the moist, which we call now the moist water content. Okay. So that's part B. We have now solved that. Okay. For part C, we are asked again to water content, or does the water content under saturated condition? So that means the degree of saturation should be 100% in that case. Okay. So to do that, we can solve first for the volume of voids, okay, wherein the volume of voids is equal to the total volume minus the volume of the soil solids. Okay, but we already know the volume of voids. Okay, that's taken from here. That's calculated from the soil sample dimensions. Then you have the volume of solids. I think we have already calculated that. Here, we know the volume of the solids. So just subtract the two will give you the volume of voids. But we know in a such condition that the volume of water is equal to the volume of voids because there's no volume of air in a saturated condition. Okay, so that means the volume of voids is equal to the volume of water. Okay. Okay. So mm, so we know that the unit weight of water is equal to the weight of water in saturated case over the volume of water. Okay. So we know already the volume of water here, multiply that by the unit weight of water, which is 9.81, then that gives you this value here. Okay. So now that we have the weight of the water in the saturated conditions, to get the saturated water content, divide that by the weight of the soil. Again, where's that weight? Soil, yeah, that's this one here, 10.65. Sorry, no, sorry, that's the total weight. Where is the weight of the soil again? Here, that's the weight of the soil. So, okay, that's 8.54. So this value divided by the weight of the soil solids, that gives you 0.283, or that's a 28.3%. Okay. So this 28.3% is the saturated water content. Okay. So this saturated water content of 28.3% is equivalent to your degree of saturation of 100%. Okay, so that means if you divide this 28.3% by 26.3% in the moist water content, no? The moist water content, then that will give you about 93%. You can try. No? Divide 26.3 by 28.3 will give you roughly 93%. This one here, the degree of saturation. Okay. So at least you can check your answer, no? Okay? So you know that bisan pag gi-checkan sa inyong teacher, kay baon na ka nga sakto imong answer dire nga 26.3 plus this 128.3, because when you check, then you go back to this 93% if you know the definition of the degree of saturation. Okay? So that's why it's important to understand the geotechnical terms. Okay? Okay, let's see. Okay, I guess that's the last slide. Okay, so we are just on time. Okay, so we still have 5 minutes left. So are there any more questions or clarifications so far? Okay. Seems that some of you are already asking very advanced questions. Okay. Okay, questions or clarifications so far? You can ask me anything. You can ask me practical questions. Okay. experiences in the field related to this one. Maybe you have encountered some problems, okay, or concerns in the field. Okay. Okay. By the way, before I forget, I think for this subject, there will be four major exams. No? You have the pre-midterm exam, the midterm exam, the pre-final exam, and the final exam. Okay, the final exam weeks. Okay, so in those weeks, I will not be giving a lecture on the Tuesdays of those weeks. Okay, so I will give the time for you to study for your major exams. Okay, yeah. So so we will not have a lecture. Okay, in those 4 weeks. Okay, and also during the I think university days. I think that whole week. Okay, I will not be giving a lecture also in that week. I think it's around October 23 to 28. I think. So that means I can probably give about 10 to 11 lectures, no? Okay, depending on uh, the available time. Okay, so that's about yeah the lectures every Tuesday. Okay, so every Thursdays again, as what we have discussed earlier, my colleagues will just give you more examples for them to discuss. Um, they can probably give you some seat works as well, no? Okay, which is also part of your grade, I think. Okay. Yeah. Okay. Okay, there are no questions so far in the chat box. Let me just stop share. Uh, okay. Are there any questions or clarifications so far? Okay. Um, yeah, I guess there's no more questions. Okay. So if there are no questions, okay, so I think we can now adjourn. Okay. So again, thank you very much for your time. Okay. Have a good night. Okay.